Okay, let's continue working through the notes for related rates. So this is the back of the handout notes, example 3. A spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area of the balloon at the moment when the surface area is 64 pi. So surface area of a sphere, we know we'll be dealing with that equation, so that is S equals 4 pi r squared. Balloon is being inflated at a rate of 10 cubic centimeters per second. So cubic centimeters, this is a measurement for unit of measurement for volume. So we know we'll also be dealing with the volume of a sphere, which is 4/3 pi r cubed. Right? We know we'll be involving the derivative of both of these equations. So we can find the derivative for v. So v becomes dv dt. Remember, each variable will now have to attach itself to a d over dt because our independent variable is now time. 4/3 pi, we can treat all of this as a leading coefficient. That's just one big number in front of the r cubed. And so we're just trying to find the derivative for r cubed, which is 3r squared. So that goes right here. And once we're involving r's derivative, we have to attach a dr over dt. Notice the 4/3 pi is just a coefficient. 3's cancel out. So we're left with dv over dt equals 4 pi r squared dr dt. Okay. And then for the surface area is 4 pi r squared. We just go ahead and find that derivative. So s becomes 1 times ds dt. So that's going to be down here. 4 pi r squared. 4 pi is the leading coefficient. That's just going to stay in place. Really, we just want to deal with is r squared. So r squared becomes 2r dr dt. And then 2r times 4 pi gives us 8 pi r dr dt. So now we have the derivative equations for both dv dt, for both the volume and for surface area. So let's see what pieces we have and what we're needing to find, and see if we can piece together this puzzle here. Okay, balloon is being inflated at a rate of 10 cubic centimeters per second. So cubic centimeters per second is dealing with rate of change of volume. So we know that 10 will be associated with the dv over dt. Okay, let's pay attention and see whether we want to keep this as a positive value. Well, the balloon is being inflated, so inflation of the balloon means that the volume will get larger over time, so we do want a positive value. Okay. At the moment when the surface area is 64 pi, okay, find the rate of change of the surface area. So we're trying to find ds over dt, which is over here. But if we want to find ds over dt, we need the radius and we need dr dt. So we're going to look at what else is available to help us get there. So let's look at what they give us here. So s equals 64 pi. We do have a formula for surface area, which is 4 pi r squared. So I can use this and the surface area equation to help me find r, and then that will help me get one of the pieces that we need for the ds dt formula. So s is 4 pi r squared. So now I can say 64 pi is 4 pi r squared. Solve for r squared. Divide both sides by 4 pi. R is equal to 4, so my radius is 4. So we have our radius, but we still need the dr over dt. Okay. Well, let's see how this dv over dt can help us. We have a value given for dv dt, which is 10 cubic centimeters per second. Radius we just found is 4. So we can now solve for dr over dt because we have these two missing information found. And then once we plug in to find dr dt, then we can use dr dt to plug in to my rate of change, or my ds over dt formula, to find this value. Okay, so let's deal with the dv over dt. The dv dt gets replaced with 10. 4 pi r squared, my r is 4, which we just found. And then we work this through here, 64 pi, divide both sides by that value. So 10 over 64 pi, that allows us to solve for dr dt. Reduce this, we get 5 over 32 pi. And now we have dr dt. We have the radius. So now with these two pieces, we can just plug in to my differential equation for surface area. So then we get 8 pi times 4 times 5 over 32 pi, exactly what we have here. And then the 8 pi times 4 is 32 pi, which cancels out with the denominator, leaving us with 5. And surface area, so that'll be square centimeters per second. All right, example 4. Joe is standing 6 miles straight east of Mo. So Joe is to the east of Mo, and they're standing 6 miles apart. Joe walks north 3 miles per hour. Okay, so Joe's walking north 3 miles per hour. Mo is walking south 1 mile per hour. At what rate is the distance between them changing after 2 hours? So let's think about the vertical change between Mo and Joe. So if he's moving 1 mile per hour and Joe's moving 3 miles per hour, the rate of change between them vertically, it will be 4 miles per hour. Okay. So what we can also do is we can just tack this onto Joe's miles per hour, and then just think of it as Mo standing in place. Okay, we're still going to get the same rate of change. We'll just transfer this motion over to Joe. That way we can have a right triangle, and with the right triangle we can relate the variables a lot better, because we'll have a better shape than this starting diagram. Okay, so let's say Mo standing in place, Joe is moving up ahead, and the 6 is staying constant. So 6 is the x, y is the vertical distance from a point to Joe, and then z will be the hypotenuse value between distance between Joe and Mo. So we talked about how the rate of change, vertical rate of change between Joe and Mo will be dy over dt, which is 4 miles per hour. We found that from doing adding 3 plus 1 together. So it says, at what rate is the distance changing between them after 2 hours? So after 2 hours, if Mo is standing still, for our sake, we're going to adjust this problem where Mo is standing still and Joe's going at 4 miles per hour. If after 2 hours, then Joe is going to make a progress of 8 miles. So 4 times 2 is 8. So if y is 8 and x is 6, then we can use Pythagorean theorem to find z, right? And so z will just be 10 miles. Okay. And so now we're trying to find dz dt, because dz dt is the rate of change, the distance between Joe and Mo. Okay. So we have a right triangle. We're going to use Pythagorean theorem to relate the 3 variables. So x squared plus y squared equals z squared. We find the derivative, 2x dx dt, 2y dy dt, 2z dz dt. And then first, we know dx dt is going to be 0 because this horizontal distance is never changing between them. So that's 0. We just start plugging everything in. 2 times y. Y is 8 miles. dy dt is 4 miles per hour. 2z, z is 10 miles. dz dt is what we're looking for. So multiply this together, we get 64 is equal to 20 dz dt. Divide both sides by 20. Simplify, reduce, we get 3.2 miles per hour is the rate of change in speed between Joe and Mo. All right, one more problem here. This problem will require similar triangles. So example 5, a conical tank, vertex down, is 10 feet across the top and 12 feet deep. So 10 feet across means the radius is 5, and we're going to use that information a little bit later. If water is flowing into the tank at a rate of 10 cubic feet per minute, So cubic feet per minute, this is dealing with volume, so we know 10 must be associated with dV dt. Find the rate of change of the depth of the water when the water is 8 feet deep. So rate of change of the depth of water, we're looking for dH dt, and at the moment when h is 8 feet deep. So the formula for a cone is pi over 3 r squared times h. dV dt is 10 cubic feet per minute because water is being flowing into the tank, so it's filling up the tank, so we know volume is going to be increasing over time. So it makes sense that we have a positive rate of change for volume. dH dt is what we're looking for at the moment when h is 8. Okay, let's think about this volume equation. If we want to find the derivative, v becomes dV dt, pi over 3 r squared h. We have two variables here, and if we want to find the derivative, we have to go through product rule. Okay, so we're not going to go through product rule, and the reason why is because if you think about this problem as it's going through product rule, a couple of things is going to be introduced into our equation. We're going to have the r, we're going to the h, we're going to have the h. We're also going to produce dr dt, and we're going to produce dH dt. Okay, so here's the thing, is that this problem produces information, gives us information about height and dH dt, but it does not provide us enough information about the radius or the dr dt for us to be able to plug in once we have the differential equation. So we're going to have to find a way to reduce the number of variables in this problem. Okay, and the way that we're going to do that is with similar triangles. Similar triangles allows us to rewrite equations using less variables, and the way we do that is similar triangles allows us to find the relationship between these two variables, between r and h, radius and height. And then we're going to use substitution to help us get our volume equation down to the variable that we need. Okay, so we're going to let's split this cone in half to create a two similar triangles, two right triangles. So let's say this is the top of the tank. We're only looking at half of it, and so we'll let this is going to be the radius of this figure of this tank, and then the height is going to be 12 feet deep. Now, as water is pouring into the tank, there's also going to be a radius of the water level and the height of the water level. So we're going to let those represent the radius and the height using variables, because that's going to be changing over time. As water is flowing in, that radius is going to be increasing in length, and the height will be increasing in value as well. The 5 and 12 will remain constant because those are the dimensions of our figure. So let's see if we can relate the two variables together with similar triangles. So similar triangles says we can do a proportion between radius and height, saying little small radius is to big radius, so r over 5 is equal to, so small radius is to big radius as small height is to big height. R over 5 is equal to h over 12. Okay, so let's look back at what we need. Okay, we have everything in terms of h and dH dt. We're trying to look for dH dt. We have h, so this gives us a clue that we don't want radius in our volume equation, because if we get rid of radius, then we have everything in terms of h, and if we have everything in terms of h, then when dH dt pops up and we have the h in, we have information that we can plug in to solve for dH dt. Okay, so we want to get rid of radius. So what we're going to do is we're going to solve for radius so that we can replace that radius in terms of height. So I'm going to do cross product. 5h is equal to 12r. Solve for r. R is equal to 5 over 12h. Okay, so we're going to rewrite volume equation in terms of h. This allows us to remove the r. So we're going to remove the r, and then in place of it, with substitution, we're going to say R is the same thing as 5 over 12h. So I'm going to rewrite my volume equation. Pi over 3 r squared h. My radius gets replaced with 5h over 12, quantity squared. So now we have our volume equation in terms of height. So we can clean this up. And once we clean this up, then we can find the derivative. And then we should have enough information where we can plug in and solve. Okay, clean this up here. Distribute the square everything inside the parentheses. We get 25h squared over 144. Multiply that by pi over 3. We'll hold on to the pi. So we get 25 pi over 432 h cubed. H squared times h gives us h cubed. So we get this to 144. Multiply this to be 432. So now we have our volume equation. Okay, everything's cleaned up. We have radius has been eliminated, and in place of it, we've adapted it in terms of height. Okay, so now we're ready to find the derivative. V becomes dv dt. 25 pi over 432 is just one big coefficient. We'll leave that outside. Okay, we just have to worry about this h cubed. So h cubed becomes 3h squared. We're involving h's derivative, so we say dh over dt. So now we should be able to solve for dh dt because we have h, which is 8 feet. We have dv dt, which is positive 10. So we plug all that in and then see if we can clean this up a little bit here. We can multiply both sides by the reciprocal and multiply the 3 and the 64 through here. So we're going to get 4,800 pi over 432. Move that to the other side. We get 432 over 4,800 pi. Multiply this through and reduce, and we're going to get 9 over 10th pi. We're trying to find dh dt, so the unit of measurement, height is in terms of feet, but then it's a rate of change, so feet per minute. Therefore, dh dt will just be 9 over 10 pi feet per minute.